In this video, we're going to explain the concept of a confidence interval. We're going to start the process by defining a seed, setting a seed so that we all get the same results. Now, the next thing we're going to do is load up the population data for females on the chow diet, and we're going to show you what the mean of that population is. It's 23.89. So that is the parameter, the truth that we are trying to estimate. Now in practice, we're going to get a sample. So here we take a sample of 30 mice, and now we get a different mean. The sample mean is not exactly the population mean as expected because it's a random variable. And what we want to do now is create an interval based on this on the 30 data points that we have that we can be pretty certain will fall on top of the true parameter, right? Which we in practice we don't know. So what we do here is we're going to take advantage of the central limit theorem. We're going to compute we're going to assume that this average, the sample average, is normally distributed. So that means that we can construct a random variable that is normally distributed, has mean 0 and standard deviation 1. So we do that. First thing to do is compute the standard error, and now we know that the mean chow minus the thing we want to know, which is this guy here, we know that this thing, let me get rid of this has mean 0. We know that the mean of the sample average is the population average, and if we divide by the standard error, then we have a normal 0-1 data, normal 0-1 random variable. So we know that that random variable 95% of the time will be between 2 and minus 2. We can be more precise than that, but just quick computation, we just put a 2 there. It's really like 1.95 that gives you exactly 95. Okay, so we know that this quantity is between this quantity is normal 0-1, and that tells us that if we create an interval with, here's the q, this is actually the number we want, it's 1.95. So that means that doing a little bit of math, we clear this out, right? We want this thing here is 95% of the time is between minus 2 and 2, really 1.95. I'm just using 2 as a rounding it off. So we know that this happens 95% of the time. Okay? Let's look at that for a little bit. That's because the thing in the middle is normal 0-1, and a normal 0-1 random variable is between minus 2 and 2 95% of the time. Right? Right? We want to be precise here. We can say minus q and q. So let's actually do that. Right, so let's put the q on top. So we know that this random, again, this interval here, this random variable here is between minus q and q 95% of the time. So if we clear out this equation so that the truth is in the middle, this guy here, we get this equation. Right, so we clear it out so that we subtract this on both sides, multiply by the SE on both sides, just doing straight. Actually, we first multiply by SE and then subtract the sample mean. We get this interval is going to be on top of the mean of the population 95% of the time. All right, so let's just create that interval. Let's look at that. And what do we have? From 22, 24, and just to corroborate here, we have that in fact it happened. It did fall on top. Right, so we can check that here. Is it true or false? And we see that it is true that it fell on top. Okay, so now we can do that several times. Make a little picture if we want. So that's what the following code is about, making a figure. So we can do it a few times, 250 times. And what we're doing is we're making a figure. Here's the truth. There it is. And what we're doing now is we're going to repeat what we just did. It's exactly what we just did. Okay, but now we're going to do it 250 times and draw an interval each time. All right, so let's just do one to see what it looks like. So we go like that. Oh, I have to make I1, and then we can see there it is. It fell on top of the truth. All right, so we can do it again, again and again. Let's do it for 2. We'll do it again, and we see the interval. There it is. It's right on top. It's not as easy to see, but there's a new line up there, and we can do this 250 times. Let's just do it 250 times, and we can see the intervals falling on top of the truth 95% of the time. The red ones, we make them red when they're not on top. So you can see this is not quite there. These aren't quite there. All right, so that worked out. The confidence interval worked out pretty well. Now let's do the same thing. Now we're going to repeat the experiment, but instead of 30, I'm going to sample 5 mice. So now, does the central limit theorem work now with only 5? Probably not. And what we're going to see, if we repeat this experiment, is that we have a lot of red lines. You can see them. There's much more than 5%, and that's because we didn't make them big enough. We didn't make the intervals big enough. The Q that we computed isn't right anymore. That Q was based on the central limit theorem. We said this is a random variable. It's normally distributed, so we can compute the Q. Let's go back up so you can see that how we use central limit theorem. See, we use Q norm. Central limit theorem tells us it's normal, so we use Q norm. It's not the case anymore, so these confidence intervals are not right. We can do it again, but now instead of defining Q norm Q with Q norm, we can use the t distribution approximation. Right, so QT now, that gives us a bigger number. We can see that it's bigger than 1.95. It's quite bigger, 12.77. And what we're going to see now is that we get bigger intervals, and as a result, we get less red. So it's about 5% red now, as it should be. And that's how the confidence intervals are constructed when you can't use central limit theorem and instead you use the t distribution. So basically all that changes really is how you compute the Q, the size of the interval as a function of the standard error, of your estimated standard error. So there you go. That's how you construct confidence interval and how they work in practice.